All right, in section 12, oh my God, in section 2.4, we're going to look at the average rate of change of functions. Basically, we're going to learn how to find the rate at which the value of a function changes as the input variable changes, as x varies. So, you are already familiar with the concept average rate of change because when we worked with linear functions, we calculated average rate of change, which was just the slope of the line going through the 2 points that we are interested in finding the average rate of change for. So when you have a linear function, no matter where you check the slope on the straight line, you're going to get the same answer because the slope is the same. So what we say is that the average rate of change is constant. So the function changes the same anywhere you look, on any portion you look. So for example, if I have this linear function, if I want to find the average rate of change between -1 and 1, for example, so the average rate of change, I abbreviate it as ARC, between -1 and 1, let's say, then it's just going to be the slope. So it's going to be the function evaluated at 1 minus the function evaluated at -1 over 1 minus -1. This is just y2 minus y1 over x2 minus x1. It's just the formula for the slope. So what is f of 1? F of 1 is 2 minus f of -1 is 0 over 1 minus -1 is 2. So the average rate of change is 1. Okay, what if I want to do the average rate of change between 1 and 4? Well, it's going to be f of 4 minus f of 1 over 4 minus 1. F of 4 is 5 minus f of 1, which is 2, over 4 minus 1, which is 3. Again, is 1, which makes sense because it's just, we said that the average rate of change for a linear function is just the slope. And what is the slope of this line? Well, if I start here, if I go up into the right one, I get to the next point, so the slope is 1. So if we wanted to get a formula for the function that is graphed in here, I know it's a linear function, so it's mx plus p. I know that the slope is 1, it's positive. So it's x plus, what is the y-intercept? 1. So now what if I want to find the average rate of change between any x and x plus h? So any 2 points on the line? So let's see, what would be the average rate of change between of x and x plus h? This is going to be f of x2, which is x plus h, minus f of x over x plus h minus x. And then you learned last time that this is called the difference quotient. So the difference quotient is just the average rate of change between x and a nearby point, adding a small quantity h to the previous point. So let's calculate. So this will be x plus h, the function evaluated x plus h. So instead of x, I'm going to have x plus h and the plus 1, minus f of x, which is x plus 1, so minus x plus 1, over h. And then this gives me x plus h plus 1 minus x minus 1 over h. The -1, the negative x, so I get h over h, which is 1. And that's no surprise that the average rate of change for any 2 points is going to be 1. Okay, so for a linear function, the average rate of change is constant, and it's basically the slope of the line. All right, what about nonlinear? What about for nonlinear functions? So when working with nonlinear functions, the average rate of change is not constant. So when you calculate the average rate of change, well, it's not constant, so that means it's changing. And what does it mean it's changing? It means it's either increasing or decreasing. Okay? So how do we find the average rate of change for nonlinear functions? The process of computing the average rate of change is the same as we are used to with straight lines. So you choose 2 points, x1 and x2, with their respective y value, f of x1 and f of x2, and then the slope of the line that goes through those 2 points, which is called a secant line, is computed, and that gives you the average rate of change between the 2 points. So let's see what I mean by that. So it's like, let's look at this parabola. Obviously it's not a line, so it's a nonlinear function. And let's see how it changes. So the function itself, if I look at this function, the function, let's call this f. The function is, if I look from left to right, the function is decreasing between negative infinity and 0. And then from 0 to infinity, the function is increasing. So the function is increasing on negative infinity 0 and decreasing on 0 to infinity. But let's see, how is the function decreasing? With what average rate of change? So if I want to find the average rate of change between negative 3 and negative 2, so at negative 3 and at negative 2, it's almost a straight line. So the average rate of change between these 2 points is going to be the slope of the line going through those 2 points. So you draw the line between those 2 points, and the average rate of change of f between those 2 points is just the slope of that line. So the average rate of change between negative 3 and negative 2 is going to be the slope. So it's going to be f of negative 2 minus f of negative 3 over negative 2 minus negative 3. So f of negative 2 is 0 minus f of negative 3. At negative 3, the function is 5 over negative 2 plus 3, that's 5. Negative 2 plus 3 is 1. So the slope is negative 5. It is a negative slope, that makes sense, so it's negative 5. Now let's see the average rate of change between negative 2 and negative 1. So I'm looking at as x increases, right? From negative 3 to negative 2, if I get closer to 0, that means that x is increasing. If I move to the right, it means that x is increasing. So let's see what are we going to get. ARC between negative 2 and negative 1 is going to be f of negative 1 minus f of negative 2 over negative 1 minus negative 2. F of negative 1 is right here. And then f of negative 2 is right here. So now I'm interested in finding the slope between these 2 points. It's kind of hard to see because it's almost linear on that portion, but we know that it's not just lines, connected lines, it's curvy. Okay, so this f of negative 1 is negative 3 minus f of negative 2, which was 0, over negative 1 plus 2, which is 1. So it's negative 3. You see, the average rate of change is not the same. It's negative 5 between negative 3 and negative 2. It's negative 3, and now, so it changed to negative 3. What about between negative 1 and 0? So the average rate of change between negative 1 and 0 is going to be f of 0 minus f of negative 1 over 0 minus negative 1. So f of 0 is negative 4 minus f of negative 1, which was negative 3, over 1. So this one is negative 4 plus 3. This one is negative 1. So we just calculated that between -1 and 0, the average rate of change is the slope of this green line. So you see, the average rate of change was this the slope of this black line, and then the slope of this red line, and then the slope of this green line. And these slopes are changing. They are not the same as it is the case for a linear function. So similarly, if I find the slope between 0 and 1, so between 0 and 1, I'm going to get that it's this slope, 0 and 1. It's this slope. So if I calculate this quick, it's just going to be f of 1 minus f of 0 over 1 minus 0, and I should be getting 1. If I find the slope between 1 and 2, it's going to be f of 2 minus f of 1 over 2 minus 1, and I should be getting 3. You should stop and do these calculations if you don't believe me. And then between 2 and 3 is going to be f of 3 minus f of 2 over 3 minus 2, and this will give you 5. So on this other side, the slope between 0 and 1 was the slope of this secant line. The slope between 1 and 2, so for 1 and 2, it's going to be the slope of this line, and then the slope between 2 and 3 is going to be the slope of this line. So what do you notice happens with the average rate of change as x increases? What did we get for the average rate of changes? We got that it was -5, and then we increased the x, we got -3, we got -1, and then we got 1, 3, and 5. So you see how the average rate of change is increasing. So the function itself was both decreasing on one portion and increasing on the other, but the average rate of change was increasing the whole time. I hope that makes sense. So on the next page, I want to look at the second graph. So this is similar to the example that we just did. So for example, for this function, I have that the function is decreasing. So decreasing, but the rate of change is increasing. So if I look between these 2 points, the rate of change is going to be the slope of this line. And then if I look between these 2 points, the rate of change is going to be the slope of this line. So basically, I have that the slope is this, and then the slope is that, and then the slope gets less and less steeper. So we say that the slope gets less and less negative, because this is a negative slope. So in that case, we say that the function is concave up. That is, the graph bends upward. So it's like it holds, if you want to think about it, like a cup of soup up. So when the rates of change are increasing, we have a graph that we call concave up. Similarly, if I have that the function is increasing, and if I look at the rates of change, so think about this like the one we did in here. It was this slope, and then it was increasing. It was getting steeper and steeper, more and more positive. So the function was increasing, and the rate of change was also increasing. So the function is increasing with an increasing rate of change. That is also a concave up. So put together both of these portions, this creates a concave up. All right, now if you have the other way, so I have that the function here is decreasing, and on this portion is increasing. But let's see what happens with the rates of change. I have the rate of change from between these 2 points is just going to be the slope of this line. And then if I let x be increased, so I'm going to look at these 2 points, and then I'm going to look at these 2 points. So what do we notice? These slopes, how are these slopes? It's like this, and then it's negative. It's like this, right? Negative. And then it gets like this. It gets more negative, and then more negative. So the slope is decreasing. And then in this case, if I have the slope right here, and then I have this slope right here, and I have this slope right here. So this slope is positive. It's very steep right here. And then it moves on to less steep but still positive, and then it moves on to less steep but still positive. So it gets less positive. So the slopes are decreasing. So the rate of change is decreasing in both of these scenarios. So this is concave down. So when the average rate of change is increasing, we have a concave up graph, and when the average rate of change is decreasing, we have a concave down. Again, this is going to come into place in calculus when we calculate second derivatives and stuff like that. So let's practice with one example, just calculating an average rate of change. So this is nonlinear. The net change between t equals 2 and t equals 2 plus h. Remember, the net change is just going to be the change in y. So the net change in y value. So the net change is going to be, if I let this be my T1 and this would be my T2, the 2 points that I'm working with are T1 and f of T1, and then T2 and f of T2. So the net change is going to be f of T2 minus f of T1. But T2 is 2 plus h, so it's f of 2 plus h minus f of 2. So let's see, f of 2 plus h is going to be 4. Instead of t, I'm going to have 2 plus h minus f of 2. Instead of t, I'm going to have 2. So this is going to give me 4 times 2 plus h squared is, 2 plus h squared is 2 plus h times 2 plus h, and you FOIL that, then you get 4 plus 4h plus h squared. And then minus 4 times 4 is 16. So then I'll get 4 times 4 is 16 plus 16h plus 4h squared minus 16. The 16 goes away, so the net change will be 4h squared plus 16h. Now determine the average rate of change between t equals 2 and t equals 2 plus h. This is just going to be f of 2 plus h minus f of 2 over h. And then I calculated at the first exercise that f of 2 plus h minus f of 2 was 4h squared plus 16h over minus f of 2, which was, no, this was already calculated, over h. And then if I factor out an h, I will get 4h plus 16 over h, and then this will give me 4h plus 16. Honestly, I don't know how much you guys are going to remember this by the time you take calculus, but this is just to get you used to doing these types of calculations. This is not going to mean too much right now, but you will see later that this is going to help you to calculate the derivative of this function at the point 2. All right, so this concludes this lecture.